All right, here we go. We are taking this and moving it down just a touch. All right, we have an equilibrium equation of nitrogen monoxide plus oxygen yields an equilibrium 2 moles of nitrogen dioxide gas. It has heat added to it, so that means that it is, Kelsey, exothermic. All right, that's going to be important with Le Chatelier's principle here. So 2NO plus O2 yields an equilibrium 2NO2 plus heat. All right, we've got to do some Le Chatelier here. We've got to predict what's going to happen if we add some oxygen. So Skylar, I'm going to add oxygen. And when I add some oxygen, there's my stress. I've done this. I've made it lopsided on one side. Which way is it going to have to now shift? I need to go towards the product side. So you can either say shifts towards the product side or shifts right. Either one is correct. So if I add oxygen, it's going to then shift to the right or shift towards products. It doesn't necessarily make it more product favored. It just means at that moment in time, because you stress the equilibrium, by adding more oxygen, it's going to shift towards the side where you are moving away from what you added. It's like taking that cake that's all nice and at equilibrium, and you put a big old clot of icing on the left side. Did you mess up the equilibrium of your cake? Yeah. You did. So you got to fix it by taking some of what you added and spread it to the other side. That's how I best get my students to understand Le Chatelier's principle, or the water in the bathtub. If I add water to the left side of the bathtub, what happens to that water? It evens out towards the other side, yes? Okay, same concept. All right, next one, Ashley. What if I remove some NO? I shift left. So now I'm at equilibrium. I remove some, I remove some NO. I've got to replace some of that NO I removed, so it's got to shift left. When you remove from a side, it's going to shift towards that side, or you could say shifts towards reactants. Okay, next one says we're going to increase temperature. So that means we're going to, Jordan, add some heat. All right, here's heat because it's an exothermic reaction. And I'm going to add some heat or add some temperature. It's going to shift left. It's going to shift away from where I'm adding the extra heat by an increase in temperature. So increasing temperature is the same thing as adding heat. You got to get that in your mind. Increasing temperature is the same as adding heat. Decreasing temperature is the opposite. You're removing heat. So it shifts left. It shifts away from wherever your heat is. All right. Big, fat, important, very important, crucial question. What happens to the value of your K if it shifts left because of a temperature change? Hayden, what did you say? Okay, how do you know it decreases? Okay. The heat is all about endo and exo. But here's one of the things we need to learn. Exothermic reactions have too much heat to begin with, so they get rid of it. Exothermic reactions have too much heat, so they get rid of it. So when you start adding more heat, when they're trying to get rid of heat, they are going to get frustrated and say, no, I don't like heat. I have to get rid of it. Don't give me more. I don't eat Brussels sprouts. Already have a refrigerator full. Do not give me more. It's what he's saying. Okay? So when heat is on the product side, they don't want it to be hot. They want it to be cold. Exothermic reactions, according to Megan from third block the other day, she said exothermic reactions are cold hardened. They like cold. exothermic reactions are cold-hearted. They like cold. That's how a lot of people use that. I like it. Do you like it? Exothermic reactions are cold-hearted. They like cold. They don't like hot. So they're not going to favor themselves. They're not going to favor their reaction being exothermic when you start adding heat. They're going to move away from product-favored reaction. In fact, it's going to cause your Kc, if you shift towards the reactant side because of a temperature change, Kc is going to decrease. Because Kc is products over reactants. If I shift it towards the reactant side, only because of a temperature change, because really heat energy is not a substance, it's energy. So I'm not really adding peanut butter to the right side of my bread because it's invisible. Heat is invisible. So that's what makes it very different. It's actually going to change the value of your Kc. So Hayden says your Kc is going to do what? It's going to be less. So that means if you lower your Kc, it's going to be less product favored. Your Kc gets smaller, your delta G gets less negative, your E cell gets less positive. Did you think about that? That little triangle, I think. Abby talked about the triangle one day, right? Okay. Okay, so Kc, delta G, and E cell are all related. I make the Kc smaller. I make the delta G less negative. I make the E cell less positive. Ever thought about that? They could ask you to write that down. And that's pretty cool. Okay. All right. Decreasing volume. Now here, how many moles of gas do I have on the reactant side total? 3. 3 moles of gas on the reactant side. Okay. How many moles of gas on the product side? 2 moles of gas on the product side. So if I decrease volume, which side is going to be favored? More moles or less moles? Less. Because think about it. A smaller volume can handle less moles better. A smaller volume can handle less moles better. It's all about the molarity with the Kcs. Moles divided by volume. So if I decrease volume, I need to decrease moles. If I decrease volume, I need to decrease moles because the molarity values be moles per liter. So I need to kind of just memorize that when I do have a change in the number of moles of gas from one side to another, decreasing volume is going to have it shift to the right here. Does it always shift right or just in this particular reaction? In this just particular reaction because I'm shifting towards the side with fewer moles of gas. So decreased volume shifts right because right side has less moles of gas. Does it change the Kc? Nope. Because what did you not change? The Kc is constant for temperatures. You change the temperatures, you change the constants. Okay, so there's a little quick review. Let's look at another review, Le Chatelier. All right, we've got ammonia plus oxygen making nitrogen plus liquid water. Oh, did you pay attention to the fact that this is liquid water? Did you pay attention to the fact that the exothermic was given to you in a different way? It's over here is delta H equals negative 1530 kJs. Okay, exothermic reactions don't like heat. Exothermic reactions don't like heat. Don't increase the temperature on an exothermic reaction and expect it to respond in a TPF manner, because it won't. It will respond in a not TPF manner if you change the temperature by adding more heat. All right. So which way, Austin, is this reaction going to go if I remove oxygen? Remove. It's going to shift to the left. Good. Abby, which way is it going to shift if I add some nitrogen? It's going to shift to the left. Mariah, what if I add some liquid water? Does that mess up the equilibrium? Liquids and solids, do they mess up the equilibrium? They don't get invited to the tasting party. So they do not affect equilibrium. My answer would be no shift. Adding a liquid or a solid has no impact on the equilibrium. Therefore, there is no shift. Now, did we get duped on that one? Okay, and understandably so, because we haven't talked about it. No shift. All right, expanding the container, making the volume bigger, Stephanie. Which way is this reaction going to shift if I make the volume larger? Which side has more moles of gas? Okay, it's going to shift left because it's going to shift towards the side with more moles of gas. And you might say, but, no buts. 2 moles of gas, 7 moles of gas. 2 moles of gas, 7 moles of gas. No buts, right? Can't count that 6 moles of water. It's liquid. Okay, final question. What if I, Kyle, increase temperature? Endo or exo? How do you know it's exo? Oh, Marie, how do you know it's exo? How do you know that? The negative sign. All right. So a negative delta H means exothermic, and increasing temperature means adding heat to the right side. Only if it's exothermic. It's endothermic if it's the left side. That means it'll be opposite from what we're talking about right now. So since the heat is going to be on the right side, because it's exothermic, adding heat is going to cause the reaction to shift. Kyle, which way? But I'm adding heat. It's on the right side. It's going to go left. So shifts, thank you, shifts left. All right, what does that do, Ira, to the Kc value if a reaction shifts left because you change the temperature? Kc value decreases. Kc value decreases. Because if it shifts left, the products go down, the reactants go up, thus that ratio is going to get smaller. But that only happens when there's a temperature change. Peanut butter on a piece of bread gets spread out evenly. So that's changing the reactant or changing the product value. But temperature is invisible. No peanut butter on the bread. So it's different. Changing temperature causes the K value to change. Changing oxygen, changing ammonia, changing nitrogen here, that doesn't cause the K value to change. Okay, so you have quiz number 1.